The universe began with a colossal pop, and every spark after that stretched into everything we know. From that moment to now, we're tracing a timeline that links you to the stars. Picture the first seconds as a hot soup cooling into atoms, the tiny blocks that later clump together to make everything, like sugar crystals waking up in tea. Those atoms learn to glow and pull on each other, birthing stars that light the night and galaxies that crowd the sky like a city at rush hour. And yes, it's big and a little silly. Imagine your morning coffee getting a cosmic upgrade. Yet this timeline helps you see how you fit into the grand story. Stay with us to travel the whole arc and discover why every sunset is a bookmark in the cosmos. The Big Bang, a cosmic dawn. In the very first moments, the cosmos was a hot, crowded soup where space itself felt almost like a rumor. There was no outside to burst into. The Big Bang wasn't an explosion in empty air, it was space stretching, like dough that swells when warm. That stretching is the birth of everything. For hundreds of thousands of years, the newborn universe was so bright and dense that light could not travel freely. Light bumped around like bumper cars. When the fire cooled enough, electrons and tiny nuclei joined to form the first atoms, mostly hydrogen and helium. Then light could travel. That moment leaves a faint glow we still study with big cameras, the cosmic microwave background, a whisper from the very early days. With time, gravity began to tug on the stuff, pulling gas into clumps that became newborn stars. Inside those stars, fusion turned lighter elements into heavier ones. When stars died, they spewed these elements into space, weaving them into future stars, planets, and even the ingredients of life. And the story moved on. The dawn wasn't a single flash, but a long warm-up that stitched the universe into a grand map of galaxies and glittering skies. We exist because of that long start. Our daily things, bread, coffee, weather, are built from atoms formed in aging stars and spread across space like confetti. The start still shapes every moment we observe. Inflation, the rapid stretch of space. Inflation is a moment when space itself grew a lot faster than anything inside it. A cosmic growth spurt that carried the universe from a tiny seed to something vastly larger. Think of air blowing up a balloon. In those early moments, the universe was unimaginably small, and then space stretched so quickly that regions now far apart could have been close neighbors before inflation started and ended. That's the core idea. Because space stretched so fast, details that seemed separate could become part of a single, simple patch, which is why the sky looks so uniform from place to place. It also hides the messy edges. Imagine you have a wrinkled sheet. When you snap it flat, small wrinkles vanish or get spread thin, and you're left with something smooth. That smoothness is a clue. Small irregularities, born as tiny bumps, were stretched to become the seeds of galaxies, like baker's bubbles that grew into loaves. That's how clumps began to form. We see those patterns when we look at the oldest light, a whisper from the very first moments that still carries the shape of the universe. It's a fingerprint. Inflation is not about breaking laws, but about giving space time to grow and stretch in a way that makes the world we know possible, without needing strange shortcuts. It's a big stretch, but gentle in comparison to possible chaos. In simple terms, think of inflating a balloon so fast that the tiny doodles on it vanish as the surface swells, and the remaining marks spread thin and even. That quick swirl created the stage for galaxies, stars, and you and me to exist. Cooling and quark soup. The universe gets cold. In the very early moments, everything was a blazing, dense soup of tiny pieces called quarks and gluons. They swirled so hot light couldn't move far. Quarks are tiny building blocks, and gluons are like glue that holds them together, making a rough, bubbly mix. It was a churning, sticky world. As the cosmos stretched and cooled a bit, the hot soup cooled enough for quarks to pair up and form the first real stuff we recognize as protons and neutrons. The crowd was shy at first. Think of sugar crystals forming as water sits and cools. The individual grains show up and join together instead of staying in a liquid blur. Electrons still zoomed around. Out of this transition came the basic recipe of matter that will later mix with light and gravity to build atoms, stars, and planets. After a while, the universe cooled enough that electrons could hug onto nuclei and form neutral atoms, freeing light to travel. The fog parted. That moment, light stopped being bounced around and began to travel across space like a well-behaved rumor, leaving behind a steady, gentle glow that we still see today. We call it the old light, the cosmic afterglow. This cooling set the stage for structure. Without it, nothing would clump. Today, scientists scan that faint glow to map the sleeping past and understand how galaxies slowly gathered their matter. The universe cooled, then listened, and the cosmos began to bloom. Nucleosynthesis, elements born in fire. Nucleosynthesis is the process by which new atoms are forged in cosmic furnaces. In the first moments after the universe began, the lightest elements were made. Most of the matter cooled into hydrogen and helium, with tiny traces of lithium left behind. No heavy metals yet, just a stretch of simple building blocks. Stars act like giant kitchen stoves where hydrogen gets mashed into helium. That fusion is a steady, glowing recipe. There are two main ways to do it: a simple path called the proton-proton chain and a faster dance called the CNO cycle, which uses carbon as a helper. Both give off energy that keeps stars bright. As stars grow older, they start to burn helium itself, making carbon and oxygen. This is like turning bricks into a new kind of building block. In smaller stars, it stops there. In giants, it keeps going. We call that stellar alchemy. When massive stars end in a fiery blast, they scatter the new elements far and wide. The core can get so hot that it pushes elements into heavier forms. This spread of material seeds planets and life, laying the raw ingredients for oceans, rocks, and you. Neutron capture, a process teenagers would call neutron snack time, crafts heavier elements in space. In a rush of cosmic fireworks, even iron and other heavy stuff get born and leave the star to drift through space. Today, we are made from star stuff. The carbon in you, the oxygen you breathe, and the iron in your blood all began life in a star somewhere. Even your phone's silicon is a cousin to the dust once hurled across the galaxy. Scientists chase the same craft in labs, trying to fuse tiny atoms here on Earth. Until then, look up and remember the cosmos gave us the recipe. Recombination, light chooses a path. In the early universe, a hot mix of free electrons and nuclei filled every corner like a crowded kitchen. Photons kept bouncing off the charged particles, unable to run free. Light could not run far, stuck in the crowd, drifting only a short hop before it met another particle. Nothing bright appeared across long distances, just a hazy glow trapped in a busy room. When the universe cooled and electrons joined with nuclei to make neutral atoms, light found a real path to travel, no longer trapped in a dense soup. This moment is called recombination. Recombination is just a fancy word for electrons attaching to atoms and letting light slip through, like zipping up a jacket so the wind stays out. The fog clears. Curious light, once tied to matter, begins to stream across space, choosing routes instead of bumping around, which means the universe becomes see-through. We can still see the glow today. The light from that era forms a foggy baby picture of the cosmos called the cosmic microwave background, a soft, even glow that wraps around us. Tiny spots in that glow map tiny bumps in density that later grow into stars and galaxies. Scientists read those spots like a fingerprint, learning where matter clumped first and how gravity nudged it into larger shapes, all without stepping into a time machine. The whole moment is a turning point, a switch from a crowded, chattering sky to a stage where light can travel far and wide. Light gets a free road, the universe gets a canvas. And every time we look up with a telescope, we are following those first photons on their long walk. A gentle reminder that a quiet decision about sharing space can change everything. The cosmic dark ages. Right after the Big Bang, the universe was a hot, chaotic soup where particles moved fast and light couldn't travel far. As it cooled a bit, protons and electrons found each other and joined up to form hydrogen, the simplest kind of atom. The seconds that followed were quiet in a strange way. The world was not yet filled with stars, so there was no real light to speak of. Light hung around as leftovers from the early heat, but it could not glow brightly. The stage was set for a long, dark spell. That spell is what scientists call the cosmic dark ages. The sky looked mostly empty and still. You could call it a space where night never ends, except for a very faint shimmer, the afterglow of the Big Bang. a soft, all-pervading light that doesn't show bright stars. It's like a room that has a small steady lamp on the ceiling after all the party lights are gone. You can see outlines, but no real brightness. Picture walking through a house where the power is flickering and the world feels hushed, almost patient. During this time, gravity did quiet work. Gas gathered into little pockets, like dough rising in a warm oven. The clumps grew denser and cooler, helping them shed heat and settle in. Tiny cooling tricks let the gas squeeze tighter until a spark of light could ignite. The first stars began to glow inside those clouds, and their glow would push photons through the surrounding fog. The moment a star lights up a cloud is like the moment a small campfire wakes a forest at night. Those early stars emitted enough energy to change the neighborhood. They knocked electrons off nearby atoms, turning quiet, neutral gas into a lively, ionized sea. The universe began to shine more as more stars and small galaxies formed, and the era of darkness gradually gave way to light. The cosmic dark ages end not with a loud shout, but with a slow brightening as the cosmos fills with starlight and the first galaxies rise from the darkness. The first stars, cosmic fireworks. In the very early universe, hydrogen and helium gas gathered under gravity into dense pockets where clouds could collapse and begin to glow. Fusion starts. These first stars were often massive and bright, burning their fuel quickly like a campfire that roars and then sighs. They carried almost no heavy elements, what scientists call metals. When these giants ended their lives, they exploded in spectacular fireworks, tossing new elements into the surrounding gas. Think of it as a chef adding spices to a pot that was missing flavor. The blasts also sent out enough light to drive electrons off atoms. A simple way to say space started to glow more. That extra brightness let light travel farther across the young cosmos. Their glow began to clear the fog that shrouded the newborn universe, letting photons roam farther than before. We call this reionization, but you can picture it as dawn lifting the mist. With the fog thinning, future stars and galaxies could form more easily and heat could reach distant corners of space. The universe grew brighter and a touch more connected. The earliest stars stitched the cosmos together by making the first heavy elements like carbon and oxygen, the building blocks of life. Your coffee, your skin, your favorite tree share a trace of those fiery beginnings. Without that magical churn of stellar fires, there would be no planets, no oceans, and no storytellers who wonder about the night. Cosmic fireworks set the stage for everything that follows. Population third stars, pristine luminous dawn. Long before our sun shone, the cosmos carried only hydrogen and helium in its gas clouds. The first stars, population third, were born from this pristine mix with no heavier elements baked into their making. Because there were no metals to help gas cool, these newborn suns grew huge, lighting up the surrounding darkness and shaping the early universe with their intense glow. In simple terms, they were the primal lamps that turned a quiet cosmos into a bright frontier. Formation happened in small pockets inside halos where gravity gathered the gas. Without metals to aid cooling, the gas couldn't break apart into many small clumps, so the clouds stayed thick and produced very large stars. These behemoths burned hot and bright, like cosmic campfire starters, pumping energy into the cradle of galaxies and helping to clear out the fog of neutral gas. Inside their fiery cores, hydrogen fused into helium and, in some cases, heavier elements as they burned. When they died, some exploded in dramatic blasts that scattered these first metals far and wide. Others collapsed into black holes or left behind compact remnants. Because we can't point to a surviving population third star, we study their fingerprints in ancient, metal-poor stars and in light from the farthest galaxies. These clues come from chemical patterns that show the influence of a star that lived fast and ended loudly, seeding the cosmos. Future telescopes and clever tricks may reveal more direct traces, giving us a clearer picture of this primal era. Reionization. The universe clears its fog. In the early universe, a fog of hydrogen wrapped the cosmos, dimming the light that tried to travel across space. The fog was real. When the first stars began to glow, their high-energy light started peeling tiny gaps in that fog, like sunlight thinning a morning mist. Things began to change. Energetic photons push electrons off hydrogen atoms, turning neutral gas into ionized gas, which means the fog becomes invisible to many kinds of light. That frees the light. Light travels more freely once the gas is ionized, so distant corners of the universe stop looking misty and instead show bright, distant things. Opening a dusty window gives a similar feel. At first, the ionized regions are small, like bubbles around a campfire, and they grow as new stars pop up and give off more light. They crowd together. Over time, these bubbles merge until most of the space is clear enough for light to sail through unimpeded. The fog thins. Scientists read the signposts of reionization in the sky using the oldest light we can access, the afterglow of the Big Bang, and by watching very distant galaxies. The clues are subtle. Some light from faraway galaxies gets soaked up by neutral hydrogen before it reaches us, leaving telltale fingerprints in the light we do see. The picture becomes brighter as the fog lifts. The timing matters because only after the fog thins can we see and study the earliest galaxies clearly. Without it, the newborn universe would stay dim and difficult to study. This is like having a sunny day after months of rain, a windshield that suddenly clears so you can spot the mountains in the distance. Science loves that moment. The process was not perfectly even, and pockets stayed foggy longer, a reminder that the universe likes to do things in its own cozy way. Even today, we map those patchy patches of light and shadow. That patchy past helps explain why some ancient galaxies look different from nearby ones, and it teaches us to be patient with cosmic timescales. The fog finally clears, and the night sky reveals its bright neighbors. Galaxy formation, seeds to giants. Gas drifts in the early cosmos, guided by invisible scaffolds of dark matter that do the heavy lifting without ever being seen. These halos act like the frames of a playground, helping gas gather where gravity wants it most. When the gas cools, it settles into a rotating disk, and stars begin to light up, seed by seed. From these humble beginnings, tiny pockets of matter grow into the seeds that will someday become full galaxies. Some of the first stars are called population third, bright and short-tempered with life because their gas has almost no metals. They blaze like quick bonfires and fade just as fast. When they die in brilliant blasts, they spread metal dust everywhere, like sprinkling glitter on a dark canvas. That metal helps the gas cool more easily, letting more normal stars form in more places. It's a bit like adding sugar to tea, making the mixture behave differently and inviting more flavors to appear. Galaxies grow not only by making new stars, but by gathering neighbors. Smaller clumps merge with one another and with budding disks to build bigger systems, a slow duet of gravity and time. The mergers can reshape a galaxy, turning a sleepy collection of stars into a bustling city of light. Some galaxies end up with graceful, flat spirals and bright central regions, while others become rounder, puffier balls known as ellipticals. Stars churn away, and new seeds of planets and clouds of gas settle into rhythm with the changing galaxy. Observations across the sky show a tapestry of disks, bulges, and halos, each telling its own story of seeds growing into giants. We see young blue regions where fresh stars are born and older, redder zones where the light comes from wiser, longer-lived stars. The journey from seed to giant is a slow climb, like a forest beginning with a few sprouts that eventually form a vast canopy. In everyday terms, it's a family tree of light, tiny beginnings that, through gathering, mergers, and a dash of cosmic luck, become the grand galaxies we glimpse across the universe. The Milky Way's early years. Gas in the young cosmos clumped under gravity into a huge, lumpy cloud that would become the Milky Way. As it cooled a bit, pockets grew dense enough to pull in more gas, and the clumps began to merge, creating a rough, chaotic shape rather than a neat disk. Stars began to flicker to life in that messy backdrop, like candles at a campfire in a dark forest. The first stars formed from mostly hydrogen and helium, the simplest ingredients. They burned fiercely and lived briefly, and when they died, they exploded, spreading heavier elements into the surrounding gas. This is how the raw material for later stars and planets got sprinkled around, a little like adding spices to a pot to build bigger flavors. The Milky Way grew by swallowing smaller galaxies and big gas clouds. Each capture stirred the system, kicking off new waves of star formation and reshaping the inner parts. It's like a city that keeps absorbing new neighborhoods. Streets twist, and the skyline changes as new kinds of stars settle in. Some of the stars from those early visitors still drift in the halo, like mementos left in an attic. Over time, the gas settled into a rotating disk, with star-forming regions concentrated in the spiral arms. Those arms act as nurseries where gas becomes stars again and again. Stars are born, live, and die, enriching the gas so later generations can form even more diverse worlds. The whole system hums with movement, a slow CD of starlight switching tracks. Today we can still read clues from those early days. Ancient, metal-poor stars in the halo tell stories of the rough beginnings, while later generations carry heavier elements and, eventually, planets. Our own sun formed from material that had already been stirred by earlier generations, a second wave of cooking in cosmic terms. The Milky Way's early years set the stage for a quiet, steady rhythm that lets life and curiosity thrive. Dark matter, the invisible scaffold. Dark matter acts as the invisible glue that keeps galaxies from tearing themselves apart. We can't see it with ordinary eyes or with light detectors, but its gravity is real, and it weighs more than the stars we can see. To explain why galaxies stay together, scientists imagine a vast halo of unseen material surrounding them. This halo serves as a hidden scaffolding that guides the formation of stars and the growth of whole galaxies. Dark matter doesn't shine, but gravity is its loud voice. In a galaxy, ordinary matter, gas and stars, feels pulled toward the center and toward the halo around it. That pull helps the disk stay intact and guides how spiral arms take shape. Without this unseen scaffold, the stars near the edge would drift away as if the rug were pulled out from under them. Think of it as an invisible frame keeping the whole picture from collapsing. Scientists infer its presence in several ways. One clue is how stars at the edge of galaxies move. They orbit faster than we would expect if only visible matter mattered. Another clue comes from gravitational lensing, which is when light from distant objects bends around unseen mass, making those objects look stretched or a little doubled. The oldest light in the universe, the cosmic glow we can still detect, also carries hints about more matter than we can see. Together, these signals point to a large invisible component shaping the cosmos. Researchers are still figuring out what dark matter is made of. The leading ideas propose new, shy particles that rarely interact with regular matter. We search for them in underground detectors, in space, and at the edges of powerful experiments. Even without a direct sighting, we track its fingerprints by watching how structures grow and move over cosmic time. Until the mystery is solved, dark matter remains the universe's invisible scaffolding, quietly setting the stage for everything else. Think of it as the universe's backstage crew, silent, sturdy, and a little mysterious. Galaxy collisions and growth. Galaxies are not lone islands. They drift through the universe in loose families. Gravity pulls them toward each other, turning a chance brush into a grand encounter. When they touch, the drama is less about clashing stars and more about gas and dust getting stirred up. Stars mostly avoid smashing into one another, like pedestrians in a crowded street, while giant gas clouds collide and churn. Tides pull on the outer edges, stretching them into long, glowing ribbons that reach into space. The whole thing reshapes the two galaxies in dramatic and visible ways. During a close pass, gravity tugs on every part, bending spins and twisting disks into new patterns. Gas clouds crash together and behave like clumpy playground foam, smashing into each other and heating up. The compressed gas lights up, giving birth to bright, young stars that sparkle along warped lanes. Sometimes the two galaxies swing past each other and settle into a slower, lingering dance, a prelude to a full merge. The cosmic show is loud in its consequences, but slow enough to feel like watching a city reassemble after a grand parade. After the clash, the galaxies often grow into a larger, more massive system. Stars from both partners mingle, and fresh stars can continue to pop into existence where gas is crowded. The central region can gulp down gas and feed the big black hole sitting at the core, turning the center into a bright beacon for a while. That glow is like a neon sign in a quiet town, a burst of activity that eventually settles. The final shape may become more rounded and calm, losing the familiar spiral arms of the originals. Yet the past shows up in tidal tails and faint streams that drift far away. These mergers keep happening across the vastness of space, not as a single event, but as a repeating pattern. They unfold over long stretches of time, each phase leaving behind clues of what came before. For us, it is a distant, slow spectacle, but for galaxies it is a quick, life-changing makeover. In the distant future, our own Milky Way and a neighbor are expected to meet and fuse into a bigger galaxy. The same story repeats as more galaxies drift together, gradually building the grand structures we observe in the night sky. The Sun, a local star. At the center of our solar system sits the Sun, a blazing ball of hot gas that keeps everything else in orbit and warms life on Earth. It's mostly hydrogen and helium. Nuclear fusion in its core turns hydrogen into helium and releases energy. That energy travels outward as light and heat. From far away it shines as a yellowish-white disk. Up close it's a roiling soup of plasma. Inside, intense pressure and temperature push hydrogen atoms together in the core. Hydrogen fuses to form helium, and that process releases energy. The energy works its way outward, eventually escaping as sunlight. The Sun is incredibly bright, far more luminous than anything we use at home. On the surface, the photosphere sits at about 500 Celsius. The surface isn't solid, it's a sea of hot gas. Above the photosphere lie the chromosphere and the corona. The corona is wild and hot, visible during eclipses as a glowing halo. Sunspots are cooler, darker patches that come and go, caused by tangled magnetic fields. They're like little weather patches on the Sun's skin. The solar wind carries charged particles into space, shaping the space around planets, and sometimes lighting up auroras near the poles. Gravitational pull from the Sun keeps the planets in their orbits, including Earth's. Earth's tilt and orbit create the seasons and set the rhythm of day and night. Distance matters, too. Sunlight is more intense when Earth is closer to the Sun and a bit gentler when it's farther away. Life depends on sunlight for warmth, photosynthesis, and mood lighting that never sleeps. Scientists monitor solar activity with satellites to protect power grids, astronauts, and our day-to-day tech habit. Because yes, sunlight is a free energy source with a lot of implications beyond a sunny afternoon. Protoplanetary disks, cradles of planets. Gas and dust swirl around a newborn star in a wide, spinning disk. This protoplanetary disk is the cradle where planets begin. Most of its mass is gas, light, and airy, while dust grains are tiny bits of rock and ice. The rotating cloud flattens into a disk, like a spinning pizza dough, with the star at its center. The heat from the young star buffets the inner regions while the outer edges stay chilly. Inside the disk, dust grains drift and collision. Often they stick, forming larger clumps. These clumps gradually assemble into pebble-sized grains, then into small rocks, all staying close to the midplane where the disk is densest. Gravity then helps them pull in more material, and a tiny seed can become a real baby planet in this cosmic kitchen. There are two main pathways to planets: core accretion, where a solid core grows and then grabs gas, and disk instability, where parts of the disk become heavy enough to collapse into a planet on their own. Core accretion is a patient builder. First you fashion a solid core, then gravity gathers gas to make a giant atmosphere. Disk instability is quicker and flashier. Swaths of gas can become gravitationally unstable and collapse, forming a giant planet without needing a slow core. Observations with modern telescopes show rings and gaps in disks, which scientists often interpret as signs of planets carving paths as they form. The exact details can vary, but the basic idea is that a disk provides both the raw material and the setting for planet building. When the disk thins and gas fades away, the newborn planets stand on their own. Some settle into neat orbits. Others end up in crowded configurations that resemble a miniature solar neighborhood. The whole process has a sense of improvisation, like bread dough that slowly rises and stretches. And it is common enough that many stars end up with their own family of worlds around them, a reminder that planets are not rare background noise in the cosmos. Planetary accretion, from dust to worlds. Dust and ice swirl in the disk around a newborn star. Tiny grains drift until they meet and stick, like Velcro in space. Ice makes sticking easier, so icy grains join forces more readily. These clumps grow into little balls, not unlike dust bunnies that shape themselves into something a bit more solid. What starts small can become the seeds of worlds. Gas in the disk slows the smallest travelers and nudges them along. Turbulence churns the mix, so collisions can be gentle or catapulting. Small grains get carried by gas toward the star, while bigger chunks sweep paths that cross others. The result is a simmering balance of sticking, breaking, and reassembling. Once a clump becomes big enough, gravity takes over and pulls in more material. These growing bodies become planetesimals, and later planetary embryos as they gather mass and clear their neighborhoods. Bigger bodies attract more nearby material, and that feedback can speed things up. Collisions between embryos are common and messy, grinding rocks into new surfaces and mixing minerals. The scene is messy yet driven by a stubborn logic. Bigger things tend to get bigger. In the outer disk, gravity can grab onto gas and form gas giants, while in the inner disk rocky planets take shape after many collisions. Planets tug on the disk as they grow, changing their paths and sometimes nudging one another closer or farther away. This movement, called migration, reshapes the layout even before everything is settled. In the end, the system holds a family of worlds with varying sizes, along with a trail of leftover rocks and ice that didn't quite become planets. Final touches come from giant impacts that melt and mix interiors and blast away debris. A famous idea is that Earth's moon formed when a big object collided with Earth, tossing material that cooled into the moon. Such events heat planets, mix their insides, and help decide what kinds of rocks show up on the surface. With time, the chaos calms, debris is cleared, and the planets settle into stable orbits around their star. The Moon and Earth, a giant impact story. In the early days of our planet, a Mars-sized world smashed into Earth, hurling a cloud of molten rock into orbit. The crash was intense. The ejected material spun around the planet and slowly cooled into a ring, then gathered into a single moon. That is the giant impact story. The moon's rocks echo Earth's outer layers, with a mantle-like chemistry and only a tiny metallic core. This is not a copy, it is a shared origin. Isotopes of oxygen in moon rocks match those in Earth, as if they were cousins who shared a family recipe. No giant iron heart sits inside the moon. Because gravity keeps pulling on them, the moon orbits Earth in a gentle, predictable way. It always shows the same face. That face is due to tidal locking, a steady hand in the solar system's dance. The tilt of our planet grew from the same crash. Over eons, tides raised by the moon slowed Earth's spin and carved seas, shaping day length and weather in playful ways. Today, the moon protects us by stabilizing our orbit, guiding tides, and giving us night light that is gentle rather than blinding. It's also a source of wonder and science class jokes. Living on a world with a neighbor that grew from our own planet's crust is like sharing a cosmic soup, where the spoonful we took became part of us. The giant impact story is a reminder that creations can come from a dramatic collision, the late heavy bombardment and volatiles. Rocks from distant corners of the solar system slammed into the inner planets and the moon, carving seas of craters and stitching a heavy patchwork across ancient rock. The sky was busy. Scientists estimate the main pulse of this bombardment happened roughly 4.1 to 3.8 billion years ago, when the solar system was still waking up and learning to behave. It was loud on a planetary scale. The travelers bringing those rocks also carried volatiles, things that love to turn into gas, like water, carbon compounds, and little organic bits. Comets and dark, snowy asteroids did the delivering. When they smashed into hot crusts, some of this stuff stuck around, seeding tiny pockets of water and the chemistry that could someday grow into life. Think of it as a damp gift from space. Over time, these deliveries helped Earth grow oceans and a hazy, warm atmosphere, turning a dry rock into a world where rain could fall. Evidence comes from ancient rocks on the moon and Earth alike that carry water in minerals and glass beads formed by impacts. The picture is not simple, but the idea is clear. The bombardment brought in water and organic pieces rather than washing everything away. That kept life's options open. In the bigger story, this period shaped how small worlds become ready to host oceans, air, and the messy chemistry life loves. For life, it was a nudge in the right direction. Today we still see the fingerprints of those early deliveries in Earth's oceans and in water-rich places we glimpse on other worlds, carried by comets and asteroids that still zoop across the cosmos. The universe left a wet stamp on our planet, and that stamp helped life start its slow, stubborn crawl toward us. Ocean worlds and early life. Water shapes the way life begins and grows. Oceans provide a stable stage where chemicals can meet and react. On Earth, the first living things learned to use the wet world to gather energy, build parts, and pass information to the next generation. Surface oceans drink in sunlight, yet the deep sea runs on a different power, chemical energy sparked by minerals from the rocks below. Water is a great solvent. It lets salts, gases, and organic molecules mix so reactions can occur more easily. Picture a kitchen where ingredients meet and stick together. In the sea, minerals from rocks act like tiny cookbooks, guiding reactions that create small, simple molecules that life can use. Some scientists imagine the earliest life using RNA, a molecule that can carry instructions and help reactions happen, like a tiny tool and notebook in one. Hydrothermal vents on the ocean floor are where chemistry gets truly energetic. They spew hot, mineral-rich water into the cold sea. Bacteria and other microbes eat the chemicals and use them as fuel. You get whole ecosystems built on chemistry rather than sunlight. Over time, more complex organisms grow, like tube-dwelling worms and clams that feed on the microbial communities. It demonstrates that life can start where heat, minerals, and water team up. Beyond Earth, ocean worlds may exist on icy moons. If there is liquid water under thick ice, tides and internal heat could keep it warm enough for chemistry to run. Energy from gravity nudging the interior could drive the same kind of chemistry you find in Earth's vents, even without sunlight. So scientists learn from Earth's seas and vent life to guess what might be possible elsewhere. If life can begin here, it could begin there as well. Maybe someday we will hear from a tiny world-hopper microbe and swap sea stories across the gulf of space. Photosynthesis. Oxygen breaks free. Sunlight powers a tiny solar-powered factory inside plant cells. Inside the green parts, chloroplasts act like small kitchens where light energy is used to split water and pull carbon dioxide together into sugar. The split releases oxygen, which simply escapes into the air. Plants do this mainly in their leaves, through tiny pores in the surface called stomata. The first part uses light to split water, producing oxygen, and to charge up little energy carriers. Think of these carriers as rechargeable batteries that move energy where it is needed. The plant then takes in carbon dioxide and uses the stored energy to assemble sugar, which it can store or use for growth. The oxygen released from water is the leftover gift, hopping out into the air. In ponds and forests, the oxygen bubbles from leaves in bright light are easy to spot. Bubbles rise and animals breathe easier. In sunlit streams, algae and tiny bacteria also do this, not just large trees. Even microscopic plants in soil and water keep the oxygen flowing. This steady oxygen release keeps air breathable and supports life on land and in water. The same process also feeds a whole food chain by making sugar that plants use to grow. When light fades, the factory slows, and when light returns, it revives. So the moment oxygen breaks free is a daily, planet-sized habit that started in leaves and now keeps life going. Eukaryotes and multicellular life. Eukaryotes are cells with a nucleus, a little library inside each cell where the DNA lives. That nucleus makes them a step up from simpler cells that drift around without a home. This big group includes plants, animals, and fungi, along with many tiny algae and water creatures. Inside, there are tiny machines called organelles that do jobs like power plants and kitchens. Multicellular life means many cells working together. This teamwork lets organisms grow bigger and do tasks that a single cell could never manage. Some cells specialize, like workers in a factory, taking on specific jobs. Leaves have cells that chase sunlight into sugar, skin cells guard the body, and nerve cells pass quick messages. They share a plan and a space, so the whole creature stays balanced. No cell wants to be the spleen, but somebody has to keep the body organized. In multicellular life, cells talk to each other through simple signals. That chatter helps tissues form, like a quilt of different fabrics sewn together. Plants grow roots, stems, and leaves, all built from the same basic cells, but each tuned to a job. Animals choreograph muscles, bones, nerves, and organs to move and feel. Fungi form networks of tiny threads that spread through food, like underground highways. Some corals live as many little bodies bound into one living colony. All this diversity comes with clever tricks and shared risks. We humans are a big team of many cells, organized into organs and systems that keep us alive. If one part falters, other parts try to help. Sickness can ripple through the body, so scientists study how to patch the system. The upside is huge. Tall trees, speedy fish, soft moss, and fungi that turn dead stuff into food. The Cambrian explosion, life explodes. During the Cambrian explosion, the oceans suddenly burst with new animal designs. They flood the scene with a stunning variety of shapes, like a crowded underwater art show. Hard shells and armor appear, protecting fragile bodies. Many lineages grow true heads, front limbs, and specialized sense organs, and eyes begin to shine in more animals. In a relatively short span, the sea fills with creatures whose bodies are neatly arranged into head, body, and tail plans. Iconic stars include trilobites, crusty sea creatures with 3 lobes on their bodies and lots of tiny legs. They lived on the sea floor and carried their own built-in armor, flipping along the sediment. There are also odd predators with big grabbing arms and wide, toothy mouths, built for snatching prey from the water. Early arthropods, the group that eventually gives us spiders, crabs, and insects, push into new ways of moving and feeding. These animals fill many roles, from scavengers to hunters. This explosion happened because several factors lined up at once. More oxygen in the seas allowed bigger bodies and tougher shells to thrive. A rise in available food, driven by more algae and little floating plants, fed more life. A genetic toolkit, with flexible instructions for growing different body parts, let animals try new shapes without inventing everything from scratch. The result is a burst of experiments, creating many shapes at once, and then keeping only those that worked best in their environments. The Cambrian explosion set the stage for most animal lineups that follow. The shells, joints, and sharp eyes we see today echo those early experiments in shellfish, crabs, and jawed fish. It matters because small changes in structure can add up to big differences in how animals live, eat, and move. Look at a modern tide pool, and you meet echoes of those early designs, fossils in a prehistoric fashion show. Evolution loves to tinker, and the Cambrian period was a loud, colorful proof of that. Vertebrates and terrestrial life. Vertebrates have a backbone that protects the spinal cord, a sturdy rod of bone or cartilage along the body. Most begin life in water. Early vertebrates were fish that breathed with gills and moved with fins. Some fish developed jaws, opening up new feeding options. That change let them bite and chew a wider range of prey. Over many generations, these jawed fish spread into fresh waters and shallow shores. A few lineages began to push out of the water and try life on land. The first 4-limbed animals are called tetrapods. Tetrapods means 4 limbs, like arms and legs that can support weight. They learned to bear weight on land and to breathe air more efficiently. Frogs and salamanders today are living cousins of those early walkers. Many amphibians begin life as eggs in water, then grow legs to explore dry patches. Their skin stays moist, which helps with breathing, but also means they need damp places. Life on land brings freedom and new dangers, from sun to predators. Amniotes arrived later. Amniotes are animals that carry embryos inside membranes that keep moisture in. This lets eggs develop on dry ground or inside the mother. Reptiles, birds, and mammals are all amniotes. Some reptiles crawl across hot sand. Others sneak through forests. Birds evolved feathers, hollow bones, and the ability to fly. Mammals grew fur, warm bodies, and the habit of feeding their babies with milk. This trio of features helps each group conquer different dryland niches. Birds are a branch that's split from dinosaurs. They keep their bodies warm with feathers and often travel long distances. Their eggs have shells that protect the developing chick. Mammals include a huge range of land animals, from tiny mice to big elephants. They nurse young with milk and often live in places where they can find food and shelter. On land, you see cats stalking through yards, dogs begging for treats, and bats catching bugs at dusk. The whole story shows how life on land grew to fit many climates, from deserts to jungles. Plant life and the land onset. Life on land started when green, algae-like beings learned to climb out of the water and try their luck on damp rocks. They found friends in fungi who could share moisture. Together, they slowly carved tiny pockets of soil and created a living bridge from sea to land. Lichens were the pioneers, a fuzzy team that could tolerate sun and wind. To survive away from the sea, plants grew a waxy coat on their surfaces that kept water from slipping away. They learned to open pores to take in air. Some stayed close to the ground, while others built simple veins to move water upward, like little plumbing networks. Underneath, roots and fungi teased soil into shape. Mosses, liverworts, and other tiny plants spread across moist ledges, forming soft green carpets. Ferns followed, unfurling their baby fronds with a slow, dramatic pop. Seed plants soon joined, bringing seeds that could wait out dry spells and sprout when rain came. With roots gripping soil, they held land together and opened food stores for animals. Today, land plants shape the world by turning sunlight into food, building soil, and coloring the landscape with forests, meadows, and gardens. A mossy rock teaches patience. They quietly do big work, from filtering water to giving us oxygen by night and day. And yes, they still surprise us with tiny after-dinner sprouts on the picnic blanket. The dinosaur era and mass extinctions. During the dinosaur era, giant reptiles ruled land, sea, and air in a warm, leafy world that lasted for millions of years. Many kinds thrived. Some walked on two legs, others on four, while enormous plant eaters browsed treetops and sharp meat eaters watched for signals in the brush. Life was busy. The stage wasn't empty beneath their big bodies. Tiny creatures scurried, clever mammals hid in burrows, and smaller reptiles plotted clever ways to survive their bigger teammates. The air was warm and the habitat changed with seasons. Forests, rivers, and coasts provided food and shelter, and different dinosaurs learned to share space, fight for a meal, and raise young even if it looked chaotic. Some wore armor on their backs. Then a turning point arrived, new risks that could wipe out big life in a short time. A huge rock crashed into the planet. The impact threw dust into the sky, blocked the sun, and cooled the world, making plants struggle and animals gasp for energy. Many species vanished. Another stress came from mountains of lava pouring out far away, steaming and choking climates, which added to the trouble for dinosaurs and their neighbors. After the dust settled, life began to rebuild in new ways. From the wreckage, new communities found room to grow, and birds emerged as modern cousins of the dinosaurs, while some small mammals found niches to survive. Fossils are like time stamps in rocks, telling us what lived and when. Today, crocodiles still carry an ancient look, and birds hop and tweet as living relatives of the dinosaurs, proof that big changes can happen while the family stays connected. The story lives on in rocks, bones, and flights overhead. So when you walk in a forest or stare at a bird perched on a branch, you're passing through a moment from a long, wild saga. Mammals rise, from shrews to giants. In the shadow of ancient giants, tiny, furry creatures skittered through leaf litter, their quiet squeaks barely louder than a whisper. These were early mammals. They hunted insects, hid in burrows, and listened for the thump of footsteps from the bigger creatures, using speed and keen senses to stay alive. Clever, unseen, they thrived on patience and small chances. Warm-blooded heat kept them comfy when weather swung cold or hot, and fur acted like a built-in coat. They nursed their babies with milk. That milk is a tiny factory inside a mother, fueling growing teeth, eyes, and curiosity. Young mammals learn fast to survive, then pass it on. Over time, some of them grew bigger, using strength, memory, and social ties to claim a safe niche. Think of elephants with their long trunks and patient feel for the herd. Whales swim in the deep sea, filling a vast space with movement and a way of life perfectly suited to water. Horses thunder across open plains, legs pumping and spirits unshackled. In forests, deserts, and oceans, mammals diversified into many shapes, from small shrews to colossal giants who carry the history of the wild on their backs. Bats flutter through the night, tiny acrobats in the sky. We share this same family, a thread of warmth, care, and clever tricks that help us all get by. From shrews to giants, the mammal story keeps moving, with new chapters written by each clever creature that dares to grow. The Ice Ages and climate shifts. Ice ages are long, cold spells when vast blankets of ice grow across many lands. Ice reflects heat like a giant mirror. As this ice expands, coastlines move inland and sea levels drop. Snow piles up year after year. Bright ice keeps sunlight from heating the ground, so summers stay cooler and weather patterns slow their pace. Life adjusts in quiet ways. Small nudges in Earth's orbit and tilt act like tiny dimmer switches for the climate. These changes arrive slowly. Some summers become warmer, allowing more ice to melt, while other summers stay cool enough to keep ice growing. Over many cycles, the balance shifts. Volcanic eruptions and fluctuations in greenhouse gases add or remove heat, nudging the system along. That is how a gentle poking can tilt long-term trends. Ice grinding through valleys and over mountains carves landscapes. Rocks get smeared and soils get mixed. When ice retreats, soils and rivers awaken, allowing new plants and animals to move in. Migration follows the changing ground. Coastlines shift as glaciers push and pull, creating new harbors and new challenges for coastal life. In the present, warmth is higher than in the recent chilly spells, and people notice shifts in rain, drought, and storms. The cause includes extra heat-trapping gases, a blanket around the planet. That blanket can make summers feel hotter and winters less biting, nudging where plants grow and where animals live. Coasts respond to sea-level pieces of the puzzle as ice melts away elsewhere. All these changes show how ice ages and climate shifts are part of a long dance the planet performs, with every turn affecting everyday life, from farmers deciding what to plant to birds choosing migration routes. The lesson is simple. Climate is big, but changes come in small steps that add up. The rise of humans, curiosity, and culture. Humans are social beings who learn by watching others and by asking questions. Curiosity is the push to understand how things work, from why the sky changes color to how a simple stone becomes a useful tool. This drive to know leads to new ideas and shared habits. Cooking, building shelters, and moving across landscapes show how curiosity turns questions into daily life. Language begins as everyday chatter and grows into a map of ideas, links between people, and plans for action. Words let communities share plans, jokes, and tips. Stories help families remember how to gather food, fix a hitch in a cart, or comfort someone when weather turns rough. A simple joke can teach more than a long lecture. Curiosity also shapes culture, the shared habits, tools, and rules that keep a group working together. Art and music carry meaning. When cooking becomes a shared rite, when a neighbor borrows a cup of sugar, or when a town gathers for celebration, culture grows from small moments. Rules keep life fair. In modern life, curiosity travels through schools, museums, libraries, and online spaces. Scientists test ideas step by step. Teachers explain with patience, and artists poke at ideas with playful experiments. Humor helps us ask better questions. The rise of humans is a long loop of asking, sharing, failing, and trying again. Agriculture and sedentary societies. Agriculture gave people a reliable source of food, turning wandering bands into communities that stay in one place. That simple shift changed daily life. People learned to plant seeds, care for animals, and harvest crops, which let homes sprout near fields. Staying put made plans possible. With a steady supply, not everyone had to chase meals. Some could specialize in making tools, weaving cloth, or tending livestock. People found new kinds of work. A blacksmith learns to shape metal while the farmer keeps barley safe and the potter crafts bowls from clay. Surplus becomes a reason to trade. Permanent homes demanded storage and order, so granaries, sheds, and simple layouts appeared to keep food safe and families together. Storage mattered. Irrigation ditches and terraced fields show how people coax water and slope into crops, even in dry spots. Farm life then has routines. Communities started to think about property, rules, and leadership as a way to protect fields and shared resources. Who owns the harvest matters. Villages developed councils, simple laws, and ceremonies that celebrate planting and harvests, tying people to land and season. Neighbors learned to share tools and seeds, and sometimes joke that the seeds grow faster after a good nap. Dense settlements also brought new problems, like waste and pests, which nudged community life towards sanitation and cooperation. Crowded living can be messy. Disease and accidents travel faster when people live close and share tools, so neighbors learn to wash hands, store water, and keep streets clean. The granary became a social center where stories were told and plans made. Agriculture did not just feed bodies. It shaped culture, art, and meaning, turning crops into stories and meals into rituals. So the settled way of life echoes in the towns we know today. Even now we see the same thread: a field, a home, a market, a shared table. The history is practical, with a pinch of humor and a lot of patience. The scientific revolution, knowledge accelerates. Knowledge began to speed up when people stopped accepting old tales as the final word and began testing ideas against the real world. They asked whether things worked and why. With simple tools, they watched, counted, and noted what happened when one factor changed. A telescope showed things the naked eye missed. Questions multiplied, and a quick experiment could prove or disprove a guess without waiting for generations. Sharing findings mattered. A printing device let words and pictures travel far, so more minds could compare notes and challenge what they heard. Ideas learned to travel faster than rumor. If light, heat, and motion could be measured and repeated, knowledge stopped floating and began to settle into useful rules. Skeptics kept the yardstick honest. Scientists built a simple recipe: ask a question, design a test, compare outcomes with predictions, and refine the idea. Precise tools helped. When experiments survived careful testing and friendly critique, they joined a growing store of shared understanding. If not, they faded away. The culture shifted from revering authority toward valuing evidence, and this change shrank the room for error. Practical progress followed. Better ideas turned into real tools for daily life, like navigational maps guiding travelers and safer medicines helping people feel better, faster. Curiosity became a habit. Communities learned to test new gadgets, share results, and adopt the best ideas so others could copy them without starting from scratch. A little humor kept the gears turning. The industrial age, energy transformed. Steam-powered machines transformed busy workshops into humming hubs where cords and gears braided into the rhythm of daily life. People learned to trust heat and pressure. Boilers heated by burning coal turned water into steam, and that steam pushed pistons to drive belts, lifts, and wheels. The factory floor woke up. Railways stitched towns together, letting heavy loads race along metal roads while schedules replaced the old rhythms of harvest and handcraft. Steam engines also made ships go faster, turning long journeys into days rather than weeks, changing maps, markets, and meals at home. Trade grew up with the whistle. In steam power, you could feel energy moving where you stood and watch the world shrink a little more each day. As ideas grew, people learned to carry energy into the dark corners of work and home with electric light and dynamic machines. Electricity is shy at first. A simple generator turned spinning magnets into power, and suddenly factories could run after sunset, and street lamps gathered crowds like fireflies. Everything felt brighter. Homes gradually swapped candles for electric lamps, and people could wash clothes and cook with steadier power instead of smoky fires. Lamps replaced flames. Power moved from a handful of boilers to a city-wide grid that fed factories, trains, and kitchens through wires, like a nervous system for a growing town. Life learned to expect light and motion at the same time. The information era, connections everywhere. Billions of data signals moved through the air and through cables, turning faraway places into everyday neighbors. Everyday chatter becomes instant. A coffee shop chat with a friend on the other side of the planet, right now. Scroll, tap, grin. Phones are tiny control hubs that carry words, maps, songs, and plans. Watches and bracelets tell us when to move. A smart fridge can ping your phone when the milk runs low. Lights change to show you've got messages. Data lives in large rooms filled with humming servers, called data centers. Your photos and notes ride these lines to stay safe. The cloud is not a fluffy thing up in the sky. It is a service that stores and moves your stuff when you want it. Open a photo in seconds. Connections everywhere help us learn faster, organize life, and share with ease. Sometimes it feels like magic. We trade ideas, jokes, and plans with strangers and friends, and the line between private and public gets a little fuzzy. Stay curious, stay kind, and keep the charger handy. Cosmic perspective, observatories and surveys. Observatories are the dedicated eyes of astronomy, designed to collect light from the night sky across different wavelengths. The atmosphere makes a messy lens. So many powerful telescopes sit on high mountains or orbit above Earth. Light at visible wavelengths shows us stars and galaxies, but infrared light can reveal hidden warmth of star-forming clouds, and radio waves trace giant structures in space. Telescopes work like giant cameras with fancy mirrors that gather tiny signals and concentrate them into sharp images. Some observatories are built with a dozen mirrors stitched together to act as one huge eye. Others ride aboard satellites where there is no air to blur the view. Even a simple backyard telescope can spark a lifelong curiosity when you spot a crescent moon or a planet. Ground-based observatories dominate in sheer size. They sit on plateaus or cliffs to get dark skies and less light pollution. A single telescope might have a huge mirror that collects faint light from faraway objects. Adaptive optics babies the image by adjusting the mirror as the air tries to blur it, like a camera stabilizer for shaky hands. Surveys are the steady workers, scanning large swaths of the sky instead of chasing a single target. They create catalogs of stars, galaxies, and other objects for researchers to study later. Spectroscopy breaks the light into a rainbow to learn what substances are present, kind of like reading the barcode of a star's chemistry. Space-based observatories sit above the atmosphere, so their pictures stay crisp. Hubble and Webb have opened new windows by looking in visible and infrared light, letting us see through dust and into stellar nurseries. They photograph galaxies, measure how fast they recede, and peek at the faint glow of ancient objects as if time travel were real. Exoplanet hunting uses subtle tricks, such as watching a planet pass in front of its star or tug on the star's motion, and space telescopes are great for that because they see more precisely. In addition to planets, space telescopes study supermassive black holes and the hot gas around distant galaxies, all to map how structures in the universe grow. Surveys like the Big Sky project stitch together enormous datasets, turning scattered light into a map of the cosmos. One mission maps the positions and motions of stars to reveal the Milky Way's shape and rhythm. Another project catalogs galaxies so astronomers can study their families and how they cluster together. These catalogs are not dusty books. They live in computers and can be searched with clever software. People can even help classify objects as citizen scientists, like sorting photos on a giveaway site. Except the subjects are galaxies and quirky stars. The data challenge is real. Big files that require smart pipelines and careful checks to avoid mistakes. All of this builds a wider cosmic perspective. We can see how light travels across the universe and how different tools confirm or refine each other's findings. The combination of ground, space, and survey work lets us test ideas about how galaxies grow, how dark matter shapes structure, and how the universe evolves without getting a single telescope muddy with rain. It also touches everyday life in small ways, from better GPS maps to advances in image processing that spin off into smartphones. The sky stops being a pure curiosity and becomes a shared resource we can explore together, one survey, one image, one upgrade at a time. Dark matter and dark energy, the unknown majority. Most of what makes up the cosmos is invisible. Dark matter and dark energy dominate the universe, yet they glow in no light at all. We know they exist because gravity acts in ways that don't fit a light-only picture, and because the universe keeps expanding in surprising, even odd, ways. Think of space as a stage dampened with hidden forces that you can feel without seeing. Dark matter acts like an unseen glue that holds galaxies together. We can't see it directly, but we can see how stars and galaxies move as if extra mass were warming the dance floor. The way light bends around invisible clumps shows up as gravitational lensing, a kind of cosmic funhouse mirror. The big map of the universe, the cosmic background light, also whispers that there is more stuff than we can see with our eyes. Dark energy is what pushes the universe to expand faster and faster. We infer this from observations of distant objects that seem to be moving away even more quickly than expected. It's like space itself has a kind of energy that acts like a gentle hand on the accelerator, nudging galaxies apart over time. We don't have a neat name for it yet, and it can feel a bit like a puzzle with more pieces than clues. Together, these unseen players make up the majority of the cosmos. Roughly 2/3 is the ever-elusive dark energy, about a quarter is dark matter, and the rest is ordinary matter, the stuff that makes stars, planets, and you. Scientists chase clues with deep underground detectors hoping to catch whispers from dark particles, with vast telescopes mapping how galaxies cluster, and with careful measurements of the oldest light in the universe. They also explore whether gravity behaves differently on the largest scales, or if new, unseen fields are at work. It's a frontier that mixes patience, clever experiments, and a bit of cosmic luck, with a sense that the best clues may be hiding in plain sight. The cosmic microwave background, a primordial map. An almost invisible glow fills the entire universe, a quiet light that feels like a baby photo of everything we see today. This light is the cosmic microwave background, a faint microwave radiation left over from the very first moments after creation. It is not red, not green, and not visible with our eyes. Think of it as heat carried by tiny waves, the kind you might notice when you nudge a microwave door and smell reheated coffee in the air. It is everywhere, in every direction, wrapping around us like a cosmic blanket. When the universe was very young, it was a hot soup of particles and light. The soup cooled as the universe expanded, and at a certain moment electrons and protons joined together into neutral atoms. That moment released photons that could travel freely for the first time, and those photons have been wandering through space ever since. If you could peek into the sky with a super-sensitive microwave camera, you would see a glow that is almost uniform, like a shy friend in a crowd, with tiny freckles of brightness here and there. Those photons are what we now call the cosmic microwave background. Those tiny freckles are a map of the early cosmos. They are not loud, just tiny differences in temperature that tell us where matter was a bit more concentrated. Where it was warmer, gravity gathered more stuff, and where it was cooler, a bit less. Imagine sprinkles and batter of cake. Little pockets of richer batter become the seeds for future cake pieces, stars, galaxies, clusters. Scientists use this map to learn what the universe is made of and how it is shaped. It helps measure how much matter and energy fill space, and whether space is flat or curved on the largest scales. Space missions have collected precise snapshots of the map, turning it into a detailed picture of the sky. The map supports our ideas about how galaxies form from those early seed variations. It shows that the quiet glow is really a doorway to the past, a simple glow that carries a grand story about beginnings and the way forward for the cosmos. Stellar endings. Novae, supernovae, remnants. A nova is a sudden brightening on the surface of a white dwarf, the dense ember left over from a star. It happens in a close pair, where gas from a companion star spills onto the white dwarf. That gas builds up pressure, and one night the surface undergoes a quick, runaway blaze. The explosion lifts a shell of material into space, but the white dwarf itself usually survives. To us, the sky might flash for a few nights and then fade, like a sparkler that seems to have burned itself out. A supernova is a colossal blast that marks a star's dramatic end. In one path, a massive star runs out of fuel and its core collapses, leaving behind a neutron star or a black hole while the outer layers are tossed into space. In another path, a white dwarf swallows fuel from a partner until a thermonuclear fuse goes off and the whole star blows apart. The blast spreads newly made elements across the galaxy, elements that will later become planets and even life. The flash can briefly outshine an entire galaxy, a cosmic firework that makes the Milky Way look a little lonely. Remnants are what's left after the blast. The ejected gas forms a glowing shell that expands and changes color as it interacts with space dust and gas. Inside, a compact object, usually a spinning neutron star called a pulsar or a hungry black hole, may shine like a lighthouse, or shoot jets that light up the surroundings. Webs of filaments glow in different colors, making beautiful shapes that amateur stargazers love to sketch. Some remnants glow in 10th ray light that tells scientists how hot the gas is and how fast it moves. All these endings play a role in the life of galaxies. The exploding material seeds the cosmos with heavy elements needed for planets and life, much like setting aside ingredients for a future meal. The remnants slow down and mix with interstellar gas, eventually forming new clouds that may birth fresh stars. For scientists, supernovae are natural laboratories where extreme physics happens, and for us they are reminders that endings can lead to new beginnings. In the grand theater of the cosmos, these stellar endings pave the way for the next chapter. Black holes and relativistic jets. Black holes are like cosmic whirlpools where gravity is so strong that nothing, not even light, can escape once it crosses the edge. The edge is called the event horizon. Gas falling toward the hole forms a bright disk that glows in 10th ray light as it heats up like metal in a forge. Far from being a simple vacuum cleaner, a black hole acts more like a busy furnace. Spinning black holes twist magnetic fields into a kind of cosmic hose, pulling in gas and shaping what happens next. From near the poles, narrow jets shoot out at speeds close to light. These jets are not streams of water, but streams of charged particles that race outward with immense power. Relativistic means their speeds are a huge fraction of light, so time and distance act a bit oddly for them. Think of a figure skater pulling in her arms and turning faster. Magnetic fields act like invisible guides, and the whole spin helps fling the gas outward along narrow paths. All this energy comes from gravity and the hot disk of gas. Jets reach across galaxies and even beyond, carving out hollow bubbles in the surrounding gas. Their impact can calm or disturb the birth of new stars. In our own galaxy, objects called microquasars show tiny versions of the same thing, with a star tugging material onto a small black hole. The basic recipe is simple. Gas falls in, magnetic fields twist, and some of that gas gets flung out. Observatories with radio, optical, and 10th ray eyes watch the jets lighting up the sky and teach us how the engines work. The structures we see can last for a long time, enduring as bright spears that shape their surroundings. And they remind us that gravity is not a silent pit, but a dynamic engine that can spit out light, particles, and huge energy. Sometimes the night sky stays quiet, and then a distant jet suddenly blasts outward, a dramatic reminder that extreme physics is always listening. Exoplanets, worlds beyond the sun. Exoplanets are planets that orbit stars beyond our sun. They are real, though tiny, and they drift around other suns across the galaxy. The simplest way we find them is by watching a star's light dip slightly when a planet passes between us and the star, a momentary eclipse. Another method catches the star's tiny wobbles as gravity from the planet tugs on it. By combining these clues, scientists learn a planet's size and orbit. They also get hints about what the world might be like. They can even guess at surface features and what the air might feel like, though that part is trickier and waits for better data. Planets come in many kinds around other stars. Some are giants sitting very close to their sun-like star, roasting in a tide of heat. Others are rocky worlds that might be Earth-like or simply larger, called super-Earths. There are puffier worlds with thick atmospheres, sometimes called mini-Neptunes. The variety is surprising, like walking into a bakery and finding cookies in every shape. It's a feast of possibilities. A key idea is the habitable zone, the region where a world might keep liquid water on its surface if the conditions are right. That's crucial because water is a basic ingredient for life as we know it. We can study an atmosphere by watching how a star's light changes as it passes through the air above the planet. When light meets molecules, some colors are absorbed, leaving a fingerprint we can read. The clouds matter too. They can hide or reveal what's below, like fog on a morning walk. If a planet has a thick, steamy atmosphere, it can trap heat and feel warmer than distance alone would suggest. Studying exoplanets tells us how common planets are and how different they can be from those in our own system. Each discovery adds a piece to the bigger puzzle of how planetary systems form. Technology keeps improving, with telescopes that collect faint signals and methods that tease out small planets. The aim isn't to copy Earth exactly, but but to understand a wide range of possible worlds. Someday we may find a world that feels almost homey, or meet a surprising alien type that challenges our ideas in a good way. The fates of galaxies and the cosmic future. The universe is still stretching its fabric like a balloon being filled with more air, and that expansion changes the fate of every galaxy. Things drift apart. In about 4 billion years, the Milky Way and Andromeda will collide and merge into a single, larger galaxy. That party lasts millions of years. Meanwhile, our sun is living its own slow clock, and in about 5 billion years it will puff up into a red giant, boiling the oceans and likely roasting any life on nearby planets. Planets may be swallowed or scorched. Colossal galaxies meet in head-on dances, stars swap places, and in the end they settle into a big, quiet blob where star formation slows. New stars fade away. The merged galaxy will keep a halo of dead suns and wandering black holes, like beads left after a party is over. Most of the glorious fireworks of star birth fade as gas is used up, and the night sky grows dimmer and more peaceful. Beyond our local neighborhood, gravity loses some of its pull as dark energy pushes space apart, so galaxies far away drift beyond the edge of what we can ever see. The cosmos keeps growing emptier. In the long run, new star formation dwindles as the available gas runs dry, so future light comes from the tired glow of old stars rather than new flames. Time keeps ticking, so the universe heads toward a quiet, even sleepy finale known as heat death, where energy is spread so thin that no sunshine remains to light a party. No fireworks, just a long, cool nap. There are more dramatic what-ifs too. Some involve the Big Rip. If a mysterious force called dark energy acts in the wrong way, it might stretch everything apart even stronger, tearing apart galaxies, solar systems, planets, and eventually atoms, like tearing a sheet of paper until nothing useful is left. That would be dramatic in a catastrophic way. Most scientists think such a dramatic break isn't likely with the energy we measure today, but it stays a cautionary tale, a reminder that the future can surprise us. For now, the safer bet is a slow fade. In the end, the fate of galaxies is not a single flash, but a long procession, a cosmic bedtime story where clusters cuddle, stars sigh, and the universe settles into a very quiet sleep. And even in that quiet, the human imagination keeps looking up with a smile. The multiverse myth, or scientific frontier. Some scientists describe the multiverse as a family of many possible worlds, not just one. The idea grows from big questions about how space and time began. In plain terms, inflation means space stretched very fast after the Big Bang, and tiny patches stopped inflating at different times, making separate bubbles. Each bubble could be its own universe with its own rules. Picture soap bubbles floating in a frothy sky, each bubble carrying a different version of reality. It sounds like science fiction, yet it rests on real math and careful reasoning. People wonder if we could ever glimpse another universe. The honest answer is no. We can't peek beyond our cosmic edge. Observations inside our universe are what we can test directly. Some theories suggest hints might show up as faint patterns in the light from the early cosmos. But none of these clues is a slam dunk. In some ideas, constants like gravity or the strength of light could differ from one universe to another. That makes the multiverse feel like a huge variety pack of possible worlds. Yet the lack of direct tests keeps it in the realm of theory. Many scientists treat it as a playground for math and imagination as much as a possible reality. It's a frontier that asks big questions with small, practical tools. Looking ahead, the frontier remains open. As instruments improve, we might tighten the bounds on what could exist beyond our horizon. Telescopes and detectors could pick up clues that steer the discussion in new directions. Scientists hope to turn the idea from a tall tale into something testable, or at least more grounded. And until then, the multiverse stays a gripping idea that makes our own universe look even more special. From a single bright spark to a sky full of stars, this is the timeline of the cosmos. Picture the very first moment when everything was a hot, crowded blur that suddenly stretched into space. It cooled, and tiny clumps of gas gathered to light up the night. Stars were born. Our sun is one of those glowing signs, a big lantern in a vast cosmic city. Around that sun, dust and gas pulled together and planets formed. One small world grew oceans and mountains, and life began as tiny sprouts that learned to grow into more complex creatures. Fast forward to humans, storytellers, builders, dreamers, who started to map the night, tell legends, and figure out how the world works. Galaxies drift like neighborhoods in a grand Milky Way, stars flicker on in different ages, and time itself stretches across billions of years. The key points are simple. The universe began, stars and planets found their homes, life found a way on Earth, humans began to understand, and curiosity keeps us going. If you watched until the end, you probably felt a little small and a lot connected, like standing at the shore and realizing you're part of the ocean's long, patient story. You're a page in this cosmic book, and that's pretty amazing. If this sparked your curiosity, tap like and subscribe for more journeys through space and time. In upcoming videos, we'll zoom into a planet's weather, peek at a star's life, peek behind a black hole's curtain, and wonder what life could be like on worlds far away. Plus how space ideas show up in everyday life, from tides to sunrise to your morning coffee. Until next time, keep looking up. Your curiosity is part of the cosmos.